Good day to everyone. My presentation will be on optimization-centric plate solar collector using Grasshopper optimization algorithm. Yeah, I'm in South Africa from the Mangosuthu University of Technology. And sorry. Yeah, my presentation will be articulated around 3 points. The first one, I'll talk about the context and the motivation of this study, and where I will talk about the flat plate solar collector. I'll talk a bit about its pipe, and I will also underline the motivation around the optimization of this study. The second point of my presentation will be around the methodology. I will present different variables that were used in this study, and also I will emphasize on the Grasshopper optimization algorithm. And the last point of my presentation will be around the results of the study and a comparative analysis between two different methods that are considered in this study. We are doing a study around the solar collector, the flat plate, but it's using semicircular heat pipe. A solar collector is a device that is used to collect the solar radiations and convert the solar radiation into heat. Then there is a absorber which is attracting the radiations. But in this case, on that absorber, we are using the heat pipe. Instead of using normal tubes, we use heat pipe because of the performance of heat pipe. And the heat pipe that I used here are semicircular or semi-cylindrical because of the contact. They create a good contact between the pipe and the absorber to increase the amount of heat that is collected. And in this study, we are considering different absorbers. There is a flat plate, there is a V-groove, and a V-trough. So we are using 3 different absorbers to see which one will perform better. Of course, considering different parameters. Now, why are we going for this method of Grasshopper? Because we have to optimize different variables. As I said, we are using 3 different absorbers, and for each absorber, we have got different parameters that we have to optimize. So we have a multi-objective system here. That's why we are going for this method of Grasshopper multi-objective optimization. As said, we have different profile of the absorbers. The first one is a flat plate absorber, where you have a flat plate that is attracting the solar radiation and where the heat pipes are installed. The second one is a V-groove. We have different V, and the solar radiations are coming on those surfaces and can be reflected at an angle of 45 to 60 degrees. That increases the area of that is attracting the solar radiations, and it will have a good impact on the output variables. The third one is a V-trough, and with the V-trough, we are concentrating the solar radiation around one surface. It also has its own advantages, and we would like to see in this study the impact of each profile on the output variables. Which are the output variables? We have 3. The one at the bottom, we will measure the heat output. We will also measure the thermal efficiency of the solar collector, and we'll also measure the thermal resistance. Now, by checking these 3, for our solar collector to be performing, the output must be maximized. The thermal efficiency as well, it must be maximized, but the thermal resistance must be minimized because the resistance is preventing the transfer of heat. for us to measure or to optimize those three variables, at the inlet of our system, we have considered three variables. At the inlet, we have the heat input, which is measured at the input of our solar collector. We have the angle of inclination and the mass flow rate. On the right-hand side of this slide, we can see the synoptics of this study. We have the absorbers and we have a multi-objective optimization system, as I said, because of the multiple variables that we have at the exit. But we have a RSM, which is the response surface methodology, which has been done already, and we will be comparing our result using the Grasshopper multi-objective algorithm to the RSM. So our study is focused on the green part of the synopsis that we have on the right. The RSM result have been produced already, but we'll do the comparison to see which one is best. And I would like here to emphasize that this is a part of a bigger study that is analyzing different approaches to see which one will give us the best result. For the study, we have generated three different models for each profile. We have the model, which was generated using the response surface methodology, and those are regression models. We can see A, B, and C are the input variables, and the input variables are the heat input, the angle, and the flow rate. And those represent A, B, and C. But the output variables, we have the heat output, HO, we have the thermal resistance, TR, and the thermal efficiency, TE. So those are the models that we will analyze for each output variable. As the method is around the Grasshopper optimization, the Grasshopper optimization is a mimic, is considering the mimic of Grasshoppers. And when we have different output or different values, the algorithm will firstly look for a global solution or global solutions in general, but after that, it will try to upgrade the position of the Grasshopper until we have the final solution that will give us the best optimum. But for us to upgrade the position of Grasshoppers, there are three different forces. There are the social force that is attracting and putting the Grasshoppers together. There is also a gravity force which is attracting the Grasshoppers on the ground, but also the air or the wind force. When the Grasshoppers are flying, the wind is affecting them. So those are the considerations to upgrade the position of each Grasshopper so we can get the optimum solution using this method. The first consideration was a single objective where we used each objective. As I showed in the previous slide, we have three different objectives. We used each single model for each absorber. And for flat plate, or when we use the flat plate only, these are the values of the optimum output. We have the maximum heat output, the maximum thermal efficiency, and the minimum thermal resistance. For the flat plate only, now, when we use the V groove, these are the values for the heat output, the thermal efficiency, and the thermal resistance. And the last one is the V draft. And we can see that by considering them individually, the V groove is giving us the best result. The output, which is maximum 155, when you compare to the flat plate and the V groove, the V draft, the thermal efficiency as well, we are sitting at 36, while the flat plate is at 19, and the V-draft is also at 19. When we consider the thermal resistance, which must be minimized, the lowest value is coming as well from the V groove. So when we consider them individually, the V groove is performing better. But as we have 3 different objectives at the exit, we cannot take them individually because of contradictions. When we increase one, it might affect the other one negatively. Or when we decrease one, it can affect the other one negatively. Then we had to go for multi-objective. We took 3 of them, the 3 objectives together, and we ran using the Grasshopper multi-objective method. After running the 3 of them together, then the V groove is also is well performing better, is giving us the heat output of 127, the thermal efficiency of 35, and the thermal resistance of 0.059. So it's still performing better, but the values have changed compared to the one that we considered individually. But it's still performing better. So at this point, we can say when we take the 3 absorbers and we run them together, the V groove is performing better. But there was another study where these equations are coming from. That study used the RSM, the response methodology. So we compare here the multi-objective Grasshopper with the response, the RSM, the response surface methods. As we can see now, by comparing the 3, the V groove is still performing better. But when we compare, for example, the efficiency of the Grasshopper and RSM, it seems like the RSM is performing better. And when we compare as well the resistance, it seems like the RSM is performing better because the thermal resistance should be minimized. But the RSM is providing good values, but these values must be understood that the RSM is taking different values on specific points. The RSM is not combining or balancing all the variables together compared to the Grasshopper. So which means though the RSM might perform better here, but it doesn't consider together all the variables. It's not combining all the variables together. It's not balancing all the metrics together. So which make us to stay attached to our Grasshopper multi-objective algorithm as the best one. Conclusion and key takeaways. As I just said it, the RSM can sometimes capture single peak metrics. It takes single peak metrics at a certain point, but it doesn't consider globally all the objectives. That's why it seems to give us some good values at some point, but at the final final result, the Grasshopper is giving the best result, and it can be very viable for design, and it can give us very promising result for design in the case of a solar collector using semi-cylindrical heat pipe. Thank you so much, and if you have questions, the floor is open. Thank you.